So for all these questions, we want to label on the forces to start with and then work out the acceleration down the slope. Okay, so for this first one, we have a force straight down, we have a force perpendicular to the plane, and we have a force parallel to the plane. We also have a reaction force in the other direction. So we have 10g down. This force here is 10g sine 10. This force here is 10g cos 10. And this reaction force, or Rn, is also 10g cos 10. So thinking about the forces down the slope, I have 10g sine 10 going down the slope, and I have no resistance to that. So I can write 10g sine 10 equals 10a. Therefore, my acceleration is g sine 10, which comes to 1.7 meters per second per second. Okay, similarly in the second question, I can label this one up like so. I have weight straight down, I have component perpendicular, a component parallel, and I have a normal reaction force. So 10g sine 20, 10g cos 20, and Rn, which is 10g cos 20. Now the reason Rn is the same in these examples is because there is no other force except for the gravitational force acting into the plane. If there was a force in here, for example, there would be a different Rn, but there isn't. Okay, we'll get to that type of question in good time. So in this case, very similar to the ones before. 10g sine 20, no resistive force, so we have 10g sine 20 equals 10a. A equals g sine 20 as opposed to g sine 10, and our acceleration therefore is 3.4 meters per second per second. Okay, when we continue with this, I'm not going to bother labeling these all up every time because it's the same method for each question. But let's go through the working. So we have 10g sine 30 equals 10a, therefore a equals g sine 30. Acceleration equals 4.9. And for the fourth one, we have 10g sine 40 equals 10a, so a equals g sine 40, which is 6.3. Okay, so as we can see here, the higher the inclination, the more the inclination, the greater the rate of acceleration. Okay, let's move on. Question 2. Okay, so we have a cyclist descending a slope, and we want to write an equation for the acceleration and show why the mass does not matter. I think we've seen, hopefully in this previous question, that in every case we cancelled the mass out. Okay, every time we cancelled the mass as we went through, and so we just had this acceleration which was to do with gravity multiplied by the angle at which it's acting. So it's going to be a similar situation in this question. If I draw my cyclist here, it's not going to be a very good drawing, I'm afraid, but we have theta, our cyclist is here, and we have straight down the mass of that cyclist, which is m, times by g to get the weight, so mg, force perpendicular to the slope, force parallel, and a reaction normal. So the angle here is theta, so this is mg sine theta, and this force into the slope is mg cos theta. Rn therefore is the same as that perpendicular force, so it's mg cos theta also. So to work out an equation for the acceleration, just like the previous question, mg sine theta is going to equal the mass times the acceleration. We can cancel out the m's, so we're left with A equals g times sine theta. Okay, and you have shown by doing that that the mass does not matter if we have a frictionless situation. Okay, question 3. We have particle 5 kilograms inclined at 20 degrees, 1.8 meters until it hits the level. Find the time it takes for it to reach the flat. Okay, well, just like in the previous questions, we're going to draw our components on first. So the first one I have is 5g straight down. Second one, perpendicular, that's going to be 5g cos 20. Parallel to the slope, 5g sine 20. Finally, label it on anyway. 5g cos 20 is our reaction normal. Okay, so the acceleration down the slope, we'll do that first. We have 5g sine 20 equals 5a. Therefore, our acceleration is g sine 20. This comes out to about 3.6 meters per second, but I'm going to use this value just to be accurate when I do my calculation. We want to find the time it takes for it to reach the bottom of the slope, and we want to know what the velocity is when it gets there. So let's start with SUVAT. I have 1.8 meters. My initial speed is 0. Final speed, we're going to find it. Acceleration I know is g sine 20. Time, we also want to find that. Okay, so you can do this in a number of ways. It's up to you really. But to work out the time it takes, we don't need to know about v. So we need to use an equation which doesn't have v in it. So we can use s equals ut plus a half at squared. This, of course, with a u value of 0, just becomes s equals a half at squared, which becomes t squared equals 2s over a. So we can put these values in. We have 3.6 divided by g sine 20. And if we square root that, we get to an answer, which is about 1.1 seconds. Okay. Second part of the question, we want to find the velocity. Now, I'm not going to use this 1.1 seconds because it's been heavily rounded. I'm going to go back to my drawing board here, and I'm going to use my v squared equals u squared plus 2as to find it. So v squared equals u squared plus 2as. Again, u is 0, so it becomes v squared equals 2as. V is therefore the square root of 2 times g sine 20 times by 1.8. And this gives me a velocity of 3.6. Now, you can do this bit of working whichever way you want. I've done it this way because I like to keep things accurate, but you could, I suppose, use the time for this one, or you could have found the velocity first and worked the other way, but up to you. Okay, question 4. Right, Baldwin Street. We have a very, very steep street, and we want to cycle up it. So the gradient is 35%, so it's a 35% hill. So the first thing we need to do is convert this into degrees. So 35% in degrees, we literally do 0.35 times 45 to find out what it is in degrees. And this gives me 15.75 degrees. Okay, so 15.75 goes here. I'm also just going to write it here, just so that we know. Okay, a cyclist is going to arrive at the bottom of the street at 50 kilometers an hour. So we also need to do a conversion for the kilometers per hour. So to do this, change it to meters, 50,000, divide it by 3,600. And I get 13.8 recurring. So let's try and keep this as accurate as possible. That's meters per second. Okay, they arrive at the bottom of the street, travelling at 13.8 meters per second. How far up the street will they go before coming to rest? Okay, right, well, let's label some forces up here. Let's pretend that our sort of intrepid cyclist is here. We haven't been told what their mass is, but as you know, it doesn't matter in this situation. The only resistive force is going to be the gravity back down the hill. So we know that we have mg this way. This component is mg sine 15.75. This component is mg cos 15.75. So we need to work out the deceleration first. So the acceleration is going to be mg sine 15.75 equals ma. So a is going to be g sine 15.75. Remember, this is a deceleration, so I am going to make it negative in the last part. We get a value of minus 2.66. And now what we need to do is work out, using a SUVAT, how we're going to do this. Now the SUVAT I'm going to use is I'm going to use v squared equals u squared plus 2as. And in this case, the v is 0 because we're coming to rest. Now what I'm going to do is I'm going to add the 2as over because we know that this a is negative. So we can write that u squared equals 2as. We can therefore write that s equals u squared over 2a. Okay, and when I put these values in, remember that u is 13.8, a is minus 2.66, although it's positive now, and we get a value of 36.3 meters. So they managed to travel 36 meters up the hill before they stop. Okay. Question B. So question B, we're saying, right, well, if it's 70 meters long, let's work backwards. How fast would you have to be traveling in order to do this? And so how we're going to do this is we're going to use, again, v squared equals u squared plus 2as. But in this case, what we're going to do is we're going to say, okay, well, we know that s must be 70. So we're going to say that they just made it to the top before they run out of sort of speed or run out of momentum. So again, v squared is 0, so we can write u squared equals 2as. We know what a is, we know what s is. So we have u squared equals 2 times 2.66 times 70. If we work this out and square root it, we get a value of 19.298 meters per second. This equates to a speed in kilometers of 69.5 kilometers per hour. And good luck to you. That's very, very fast, okay? So to ride a bike very, very fast to the bottom of the hill, you may just make it up, but not likely. Now, this question is a little bit kind of unrealistic, and And for what reasons? Well, the main reason is air resistance. Okay, there will also be some rolling resistance, so there will be some friction. And that friction comes from the bearings of the bike. We may not stay in a straight line. That's the other thing. You'd have to cycle up perfectly in a straight line. The gradient may not be completely consistent, so you might have a inconsistent gradient. You could imagine if it's slightly steeper to start with, then it's less steep, then it's a bit steeper. This bit of gradient is going to scrub a lot of speed off straight away. If the average gradient is 35, you know, it's going to be difficult. But I suppose what you could think is, if it's less steep to start with and steep at the end, you may just about make it. Yeah, you can improve in lots of ways. Okay, question 5. This question a little bit more straightforward, I think. We have a 200 kilogram particle, 40 degrees, force of 1,500 newtons is applied. So let's find out what happens to this particle. As usual, draw our forces on to start with. 200 G down. (40 degrees in here). 200 G cos 40. 200 G sine 40. Hopefully getting really used to labelling this up and being confident with it. We have Rn here, which is 200 G cos 40. And now we need to think about our point diagram. So let's draw a point diagram. Right, what's happening down the slope? Well, down the slope, we have 200 G sine 40. Up the slope, we have 1,500 newtons. Okay, so it's worth sort of working out roughly what this one is to start with. So all I'm going to do is I'm just going to do 200 times 9.8 times sine 40 and see, okay, it's less than 1,500. So what I know is that it's going to go this way. It's going to go up the slope. Now, you don't necessarily have to do that, but it's easier to find out before to work out what's going to happen than find out afterwards. And the way you'd find out afterwards is perhaps just by finding a negative value. And that's not always going to be the best way to find out what's going on. So work it out briefly to start with, and you'll know. So F equals ma. We have 1,500 subtract 200 G sine 40 because the 1,500 is bigger. We have ma. Which is 200a. 1,500 subtract this, divided by 200, gives me a very small acceleration of 0.57. So it's going to accelerate up the slope, but not at a particularly high rate. Okay, question 6. We have the knockoff vehicle, the Earth Raver. Quality bit of kit, and it's going up a slope to here. It's going to briefly stop. Okay, it's going to get to the top and stop very, very briefly, and then it's going to come back down this side. So let's split this into two journeys. Let's look at the first one. So I'm just going to draw a kind of broken up diagram over here. So I'm just going to draw a bit of the plane over here and a bit of the plane over here. Okay. So on this side, here's my car. As you can tell, it's a car. And we can work out the accelerations or the forces on it. So the vehicle is 1,800. So 1,800 G. Acting against it is 1,800 G sine 10. And 1,800 G cos 10 acts into the slope. Okay. So let's label on the force it generates. It generates 7,000 newtons of force. How long does it take to reach top of the hill? Okay, let's do this part first. So Going up the hill is 7,000, so we do 7,000, subtract the gravitational component down the hill, which is 1,800 g sine 10. This equals 1,800 a. The acceleration comes out to 2.187. And thinking about our SUVATs, well, we know that it's 200 meters long. We know that we've got a U value of 0, so let's label these on SUVAT. So S is 200, U is 0, V doesn't matter, no, we don't need to know. Let's just put it as V. Acceleration 2.187, and T is what we're trying to find. So we're going to use S equals UT plus a half AT squared. We're going to reduce down this formula. So we get rid of UT because it's 0. We rearrange this and we get that T is the square root of 2S over A. Put in the values. So we're going to put in 2S is going to be 400 divided by A, which is 2.187. And this gives us a time of 13.5 seconds. So 13.5 seconds to get up the slope. Okay, on the descent, the car must descend safely. The driver is going to engage a gear, which means that it provides resistance to the motion. So basically what we're saying is we're putting the car in a gear, which means that it can only sort of crawl down the hill. Now, I don't claim to be someone who knows anything about driving four-wheel drive, so I drive a Skoda. So I'm taking this as red, but you do have gears which reduce your speed. They create mechanical resistance in the engine, which stops you going out of control. So let's have a look at the slope going down. So the car here, 1,800. It has a force here working against it. That's the engine. We have the weight down. Don't need to worry about this component. This component is 1,800 G sine 20. It's 20 degrees now, not 10. Okay, so we need to draw this up. So we have the force down from gravity is 1,800 sine 20. Subtract this FR, okay, this engine force, or this sort of retarding force, this frictional force, against it, and that must equal 1,800 times by A. Now the question is, what is A? Well, we need to work out A because we need to work out what's the acceleration or the deceleration that it needs to have in order for it not to go sort of over 5 when it gets to the bottom. So to do this, we just need to work out a SUVAT to work out what the acceleration is and then put it back in. So the distance is 100 meters. U is 0 to start with. V is 5. Okay, so we're going to say it is 5. That'll give us a kind of minimum force. Acceleration is what we're trying to find, and we don't need T. So we're going to use V squared equals U squared plus 2AS. U is 0. The acceleration therefore must be V squared divided by 2S, which is going to be 25 over 200. This gives me 1/8, or in decimal 0.125 ms to the minus 2. So the acceleration must be at most 0.125. So let's put this back in here. So on this side we have 1,800 times 0.125. This side stays the same. Okay, so our FR therefore is going to equal 1,800 times by 0.125. Subtract, I've got that right? No, other way around. we add the FR over. So we add this to this side. So it's going to be 1800 G sine 20 subtract 1800 times 0.125. That's better. Okay, so what we're saying is we have the force down the slope, okay, and we're subtracting the acceleration from that. Okay, so the resistive force must be this when you work it out, and that gives me 5,808.24 newtons. So the force must be greater, let's think about it, must be greater than 5,808. Let's put 0.2 newtons, okay? So if we have a force greater than that, we're going to get to the bottom less than 5 meters per second. Okay, but if we apply a force of 5,808 newtons, we get to the bottom at 5 meters per second. Okay, so we want the force to be bigger than that.